All right, so we are going to do drag force today. As you may have seen in the reading, drag force is going to require calculus because the amount of force changes depending on how fast you're going. So it's a resistive force. That depends on velocity. So the book had a thing with had a diagram with the falling cat. Maybe they listened to that podcast on Radiolab. Falling cat initially has a force of gravity pulling it straight down, but the drag force going up initially is essentially zero. But then sometime later, force of gravity, which is still the same, but there's an upward force, air resistance, or the drag force. And if the cat falls far enough, is falling long enough, then the drag force will cancel out the force of gravity, and the cat is in terminal velocity. Very good. Terminal velocity. When the drag force is equal to the force of gravity, because once the forces are balanced, what's the acceleration? Zero. So the velocity is constant. But we are not going to deal with a complicated situation such as this. We're going to do something a little bit simpler. But first, let me give you an AP aside. AP aside. Our textbook defines the drag force as this pretty crazy complicated formula. Is that e to the a v squared? See, is it EAV squared? Is that it? Something like that? It's just crazy complicated formula, and to have to go through and define these things and get them all, it's really messy. The AP exam never requires you to do something like this. They greatly simplify the formula by combining a lot of the terms. And on the AP exam, if they ask a drag force question, which they tend to do every 2 to 3 years, it would be something like this. The drag force is equal to negative b v squared. Or they might do it like this, negative b v. This is, of course, the simpler of the two equations, but in years past, they have presented it. They've basically combined all these things into one term and said, all right, in terms of, I think the v squared goes on the bottom. But you're not going to have to use this. I'm not going to have you do homework problems using all this stuff. We're going to stick with the simpler version that the AP exam would most likely give you. So again, they combine all these things into one constant, and they just call it B. And they'll call it the drag constant, or the drag coefficient. All right, so the situation we're going to look at is a box on a frictionless plane. Because physicists love blocks. It's a level box on frictionless surface. And of course, if there was no air drag and the box had a velocity, it would just maintain that velocity. But with the drag force, it's going to be slowing down. So let's just assume that it's a drag force of V, minus kV. How do we analyze this problem? Where do we start? Stay mentally flexible. Sometimes the AP exam has done minus B, sometimes minus K. Just know that they put in some constant instead of all that other messy stuff. So how do we analyze this? We're dealing with forces. Where do we start? Okay, so do we need to consider the force of gravity or the normal force? Are those going to be contributing at all to the acceleration? No, because it's frictionless. There are no forces we have to consider in the y direction. So all the forces are going to be in the x direction. What is the force in the x direction? The drag force. That's it. And that's going to cause the mass to accelerate. Now the difficulty here is that as the acceleration changes, the force is going to change. Because we have minus v equals ma. Both of these terms depend upon a. They change with time. So in order for us to analyze this, we're going to have to do calculus. You would get a graph that looks something like this. With time, the net force is going to change. And what kind of relationship do you think this is going to be? It's going to be an asymptotic. It's an asymptote. So in a perfect world, it would forever be slowing down, but never actually reach zero. Of course, in real life, it would eventually reach zero. But all right. So what do you think is the next step? Well, here are the goals. These would be typical goals asked on the AP exam. Find VT, x with respect to t, and acceleration with respect to t. So these would be typical questions to ask. So we'll start again. We brought it to this point. Newton's second law, always a good place to start if you are dealing with forces. So minus kV equals ma. What are we going to do next? We are going to substitute instead of a, because both of these are with respect to t, so we're going to put this in terms of v, because a is equal to dv dt. So minus kv is equal to m dv dt. This is called a first order differential equation. First order differential equation. The way you solve the first or any differential equation is really very similar, at least from the perspective of the AP Physics C exam. They're never going to give you extremely hard differential equations to solve, but something along these lines. By the way, why do you think they call it a differential equation? Take a guess? It's got a derivative in it, so it's a differential equation. As soon as you put a derivative in it, it becomes a differential equation. All right, so what we want to do, the rules of solving a first order differential equation are, number one, put like terms and variables on the same side of equation. Put the like terms and variables on the same side of the equation. So we're going to take the dt, bring it over here. We're going to take the v, bring it over there. So we can multiply both sides by dt, divide both sides by v. So I'll have minus k dt is equal to m over v dt or dv. Now looking at these two, when we go to, we're going to be integrating. When we go to integrate, it's usually beneficial to get all the constants onto one side of the equation. M is a constant. The mass of the box is not changing with time, so I'll bring it over here. Divide both sides by M. Divide both sides by M. So I get the following. Minus K over M dt is equal to 1 over V dV. The reason I brought it over to this side is because this side is going to be easier to integrate. It's fairly straightforward. So I bring the constants over to that side. Here I'll try to get the variables by itself. This is where you take out, if you're not terribly familiar with calculus, we're going to be, to get rid of the derivative, we take the integral, because the integral is really just a reverse derivative. So we're going to integrate both sides. And we have to take our limits. So we're going to start at time equals 0. T0 equals 0. Sometime later, we'll just call sometime later. And we're also going to go from V0 to V. Now, when doing integrals, the nice thing about the AP exam is it's really a baby calculus. You never have to do, the hardest thing you'll ever have to do is a U substitution. In this case, we're going to be using this integral and this integral. This one will be for the dt side, and this one is for the 1 over V side. So the constants factor out, minus K over M. And I have the integral from 0 to t of dt. V0, V, 1 over V, dV. If you look at the list, or at the shortcuts, what would the integral of this become? Yeah, it just becomes t. From 0 to t. The integral of this one becomes the natural log of V. And that goes from V0 to V. So these things right here mean it's a range. So you would rewrite it Km T minus T0. But T0 is really just 0. So T minus 0 is not important. And the natural log of V minus natural log of V0, which there is a identity that makes this natural log of V over V0. Now what? We're looking to solve for Vt. Solve for V with respect to t. So how are we going to get this V by itself? An E, you mean? Yeah. If you take the E of both sides, E minus K over M T is equal to, if you do the E of natural log V over V0, this just becomes V over V0. So if you take the E of both sides, you're going to get this by itself. V over V0. Multiply both sides by V0. So you get V is equal to V0 E minus K over M T. And that's it. That's the solution for V. Which, the graph that we were guessing before, as time goes on, the force is going to be shrinking because the velocity is going to be shrinking. The drag force will be shrinking, so the velocity will be shrinking. If you were to graph this out, you would get that graph with time.